The Gemini 1.5 Report by Zvi Mowshowitz. This post goes over the extensive report Google put out on Gemini 1.5. There are no important surprises. Both Gemini Pro 1.5 and Gemini Flash are highly capable multimodal models, incorporating a novel mixture of experts' architecture and various other improvements. They are solid models with solid performance. It can be useful and interesting to go over the details of their strengths and weaknesses. The biggest thing to know is that Google improves its models incrementally and silently over time. So if you have not used Gemini in months, you might be underestimating what it can do. I'm hitting send and then jumping on a plane to Berkeley. Perhaps I will see you there over the weekend. That means that if there are mistakes here, I will be slower to respond and correct them than usual, so consider checking the comments section. Practical questions first. The practical bottom line remains the same. Gemini Pro 1.5 is an excellent 4-level model. Its big advantage is its long context window, and it is good at explanations and has integrations with some Google services that I find useful. If you want a straightforward, clean, practical, just the facts output and that stays in the no fun zone, then Gemini could be for you. I recommend experimenting to find out when you do and don't prefer it versus GPT-4o and Claude Opus, and will continue to use a mix of all three and keep an eye on changes. How is the improvement process going?
IMSIS.org. Big news. Gemini 1.5 Flash, Pro, and Advanced results are out. Gemini 1.5 Pro Advanced at number 2, closing in on GPT-4o. Gemini 1.5 Flash at number 9, outperforming Llama 370B and nearly reaching GPT-40125. Pro is significantly stronger than its April version. Flash's cost, capabilities, and unmatched context length make it a market game changer. More excitingly, in Chinese, Gemini 1.5 Pro and Advanced are now the best number 1 model in the world. Flash becomes even stronger. We also see new Gemini family remains top in our new hard prompts category, which features more challenging problem-solving user queries.
Here is the overall leaderboard.
First place, GPT-4o 2024-0513, ELO score 1287. Second place, Gemini 1.5 Pro API 0514, ELO score 1268. Third place, Gemini Advanced 0514, ELO score 1267. Fourth place, Gemini 1.5 Pro, APT 0409 Preview, ELO score 1258. Fifth place, GPT-4 Turbo 2024-0409, ELO score 1256. Sixth place, GPT-4 1106 Preview, ELO score 1252. Seventh place, GPT-4 0125 Preview, ELO score 1246. Eighth place, Claude 3 Opus, ELO score 1248. Ninth place, Gemini 1.5 Flash API 0514, ELO score 1232. 10th place, Large Preview, ELO score 1239. 11th place, Llama 370B Instruct, ELO score 1208. 12th place, Bard Gemini Pro, ELO score 1208. 13th place, Rekka Core 2002-40551, ELO score 1201.
Oriel Vinyals, VP of Research DeepMind. Today we have published our updated Gemini 1.5 model technical report. As Jeff Dean highlights, in the full report this post analyzes, we have made significant progress in Gemini 1.5 Pro across all key benchmarks. TLDR, 1.5 Pro, 1.0 Ultra, 1.5 Flash, our fastest model. 1.0 Ultra. As a math undergrad, our drastic results in mathematics are particularly exciting to me.
As an overall take, the metrics in the report say this is accurate. The Arena benchmark suggests that Flash is not as good as Ultra in terms of output quality, but it makes up for that several times over with speed and cost. Gemini 1.5 Pro's Arena showing is impressive, midway between Opus and GPT-4o. For my purposes, Opus is underrated here and GPT-4o is overrated, and I would have all three models close. All right, on to the report. I will start with the big Gemini advantages. Speed kills. One update I have made recently is to place a lot more emphasis on speed of response. This will be key for the new conversational audio modes and is a great aid even with text. Often lower quality is worth it to get faster response, so long as you know when to make an exception. Indeed, I have found Claude Opus, for my purposes, usually gives the best responses. The main reason I still often don't use it is speed or sometimes style, and occasionally Gemini's context window. How fast is Gemini Flash? Quite fast. Gemini Pro is reasonably fast too.
Gemini 1.5 Flash, English 1.5, Japanese 4.3, Chinese 5.2, French 1.9. Gemini 1.5 Pro, English 4.3, Japanese 10.9, Chinese 14.1, French 4.7. GPT 3.5 Turbo, English 2.6, Japanese 12.9, Chinese 18.4, French 4.1. GPT-4 Turbo, English 6.8, Japanese 35.4, Chinese 53.4, French 10.7. Claude 3 Haiku, English 2.2, Japanese 10.7, Chinese 12.8, French 3.0. Claude 3 Sonnet, English 6.2, Japanese 23.9, Chinese 30, French 6.8. Claude 3 Opus, English 10.5, Japanese 46.6, Chinese 55.3, French 13.4. Table 3. Time per output character, MS, of various APIs for English, Japanese, Chinese, and French responses, given inputs of 10,000 characters. Gemini 1.5 Flash achieves the fastest output generation for all languages tested.
GPT-4o is slightly more than twice as fast as GPT-4 Turbo, making it modestly faster than Gemini 1.5 Pro in English. Very large context. Windows one place. Google is clearly ahead as context window size. Both Pro and Flash can potentially handle context windows of up to 10 million tokens.
Figure 1. Gemini 1.5. Pro achieves near-perfect needle recall, greater than 99.7%, up to 1 million tokens of haystack in all modalities, i.e. text, video, and audio. It even maintains this recall performance when extending to 10 million tokens in the text modality, approximately 7 million words, 9.7 million tokens in the audio modality.
The actual upper bound is that cost and speed scale with context window size. That is why users are limited to 1 to 2 million tokens, and only a tiny minority of use cases use even a major fraction of that. Relative performance within the Gemini family. Gemini 1.5 Flash is claimed to outperform Gemini 1.0 Pro, despite being vastly smaller, cheaper, and faster, including training costs. Gemini 1.5 Pro is claimed to surpass Gemini 1.0 Ultra, despite being vastly smaller, cheaper, and faster, including training costs. Google's strategy has been to incrementally improve Gemini and previously Bard over time. They claim the current version is substantially better than the February version. Here they use win rates on various benchmarks. The relative text and vision win rates are impressive.
Table 1. Gemini 1.5. Pro win rates compared to Gemini 1.5 Pro from the February release, as well as the Gemini 1.0 family. Gemini 1.5 Pro maintains high levels of performance even as its context window increases. Table 2. Gemini 1.5. Flash win rates compared to Gemini 1.0 family. Gemini 1.5 Flash, while being smaller and way more efficient and faster to serve, maintains high levels of performance even as its context window increases.
On audio, the old 1.5 Pro is still on top, and 1.0 Pro is still beating both the new 1.5 Pro and 1.5 Flash. They do not explain what happened there. There are several signs throughout that the audio processing has taken a hit, but in 9.2.1 they say, efficient processing of audio files at scale may introduce individual benefits, and generally seem to be taking the attitude audio performance is improved. It would be weird if audio performance did not improve. I notice confusion there. Here is a bold claim.
In more realistic multimodal long-context benchmarks which require retrieval and reasoning over multiple parts of the context, such as answering questions from long documents or long videos, we also see Gemini 1.5 Pro outperforming all competing models across all modalities, even when these models are augmented with external retrieval methods.
Here are some admittedly selected benchmarks.
Figure 2. Comparison of Gemini 1.5 Pro, May 2024, to the initial version, February 2024, across several benchmarks. The latest Gemini 1.5 Pro makes improvements across all reasoning, coding, vision, and video benchmarks, with audio and translation performance remaining neutral. Note that for FLURs, a lower score is better.
Gemini Flash and the future Flash 8B. Gemini Pro 1.5 is neat. Depending on what you are looking to do, it is roughly on par with its rivals Claude Opus and GPT-4o. Gemini Flash 1.5 is in many ways more impressive. It seems clearly out in front in its weight class. On Arena is it in a tie for 9th, only slightly behind Claude Opus. Everything ranked above it is from Google, Anthropic, or OpenAI and considerably larger, although Flash is established as somewhat larger than 8B. The new Flash 8B is still under active development, aimed at various lightweight tasks and those requiring low latency. The question here is how close it can get to the full-size Flash. Here is where they are now.
GPQA, graduate level Google Proof Q and A. 1.5 Flash 8B, 30.8% zero shot. 1.5 Flash, 39.5% zero shot. Math problems ranging across 5 levels of difficulty and 7 subdisciplines. 1.5 Flash 8B, 35.9% 4-shot Minerva prompt. 1.5 Flash, 54.9% 4-shot Minerva prompt. Big Bench, hard, a subset of harder tasks from Big Bench formatted as COT problems. 1.5 Flash 8B, 69.5% 3-shot. 1.5 Flash, 85.5% 3-shot. MMLU, test, multiple choice questions in 57 subjects, professional and academic. 1.5 Flash 8B, 68.1% 5-shot. 1.5 Flash, 78.9% 5-shot. Natural 2 code, chat preamble, metric, pass rate. 1.5 Flash 8B, 67.6% 0-shot. 1.5 Flash, 77.2% 0-shot. MGSM, multilingual math reasoning. 1.5 Flash 8B, 70.5% 8-shot. 1.5 Flash, 82.4% 8-shot. Covos 2, automatic speech translation, 20 languages. Metric, blue, upward arrow. 1.5 Flash 8B, 24.90 shot. 1.5 Flash, 36.10 shot. MMMU, Val, image-based, multidiscipline, college-level problems. 1.5 Flash 8B, 50.3% 0 shot. 1.5 Flash, 56.1% 0 shot. Doc VQA, visual QA on documents with text and non-textual elements. 1.5 Flash 8B, 73.6% 0 shot. 1.5 Flash, 88.8% 0 shot. Text VQA, visual QA on text within images. 1.5 Flash 8B, 66.7% 0 shot. 1.5 Flash, 78.7% 0 shot. VEDEX, test. English video captioning. Metric, CIDR. 1.5 Flash 8B, 53.24 shot. 1.5 Flash, 57.14 shot. Table 22. A sampling of evaluation results comparing Gemini 1.5 Flash 8B and Gemini 1.5 Flash models on a few standard evaluations spanning capabilities and modalities. Unless otherwise stated, we report accuracy. All numbers are obtained after instruction tuning, as described in Section 4. That is a clear step down, but it is not that large a step down in the grand scheme if these are representative. especially if Flash 8B is focusing on and mostly used for practical efficiencies and the most common tasks. Comparing this to Llama 8B, we see inferior MMLU. Llama 3 was 66.6, but superior Big Bench, Llama 3 was 61.1.
New and improved evaluations. Section 5 on evaluations notes that models are becoming too good to be well measured by existing benchmarks. The old benchmarks do not use long context windows. They focus on compact tasks within a modality and generally are becoming saturated. A cynical response would be, that is your excuse that you did not do that great on the traditional evaluations, and also that lets you cherry-pick the tests you highlight. Those are highly reasonable objections. It would be easy to make these models look substantially better or up to vastly worse if Google wanted to do that. My presumption is they want to make the models look good, and there is some selection involved, but that Google is at heart playing fair. They are still covering most of the normal benchmarks, and it would be easy enough for outsiders to run such tests. So what are they boasting about? In 5.1, they claim Gemini 1.5 Pro can answer specific queries about very large 746K token codebases, or locate a scene in Les Miserables from a hand-drawn sketch, or get to the second time stamped information about a 45-minute movie. How quickly we get used to such abilities, ho-hum. None of that is new. In 5.2, they talk about evaluations for long context windows, since that is one of Gemini's biggest advantages. They claim 99.7% recall at 1 million tokens and 99.2% at 10 million for Gemini Pro. For Gemini Flash at 2 million tokens, they claim 100% recall on text, 99.8% on video, and 99.1% on audio. I notice those don't line up, but the point is, this is damn good recall, however you look at it. In 5.2.1.1, they find that knowing more previous tokens monotonically increases prediction accuracy of remaining tokens within a work up to 10 mem tokens. Not a surprise, and unclear how to compare this to other models. Label your y-axis.
The charts show the cumulative average negative log likelihood, NLL, for different versions of the Gemini model, 1.5 Flash, 1.0 Pro, and 1.5 Pro, over varying sequence positions for long documents, left chart, and code, right chart. The x-axis represents the sequence position on a logarithmic scale, while the y-axis represents the NLL. The power law fit is shown as a dashed line. For both long documents and code, Gemini 1.5 Pro achieves the lowest NLL, indicating better performance, followed by Gemini 1.0 Pro and Gemini 1.5 Flash. The high R-squared values, 0.997 and 0.995, suggest a strong fit of the power law model to the data.
In 5.2.1.2 and 5.2.1.3, they do text and video haystack tests, which go very well for all models tested, with Gemini 1.5 Pro extending its range beyond where rivals run out of context window space. In the video test, the needle is text on the screen for 1 frame. In 5.2.1.4, they do an audio test, with the keyword being spoken. Even up to 107 hours of footage, Gemini Pro gets it right every time, and Flash scored 98.7%, versus 94.5% for Whisper plus GPT-4 up to 11 hours. This was before GPT-4o. This is clearly a highly saturated benchmark. For 5.2.1.5, they test hiding multiple needles within the haystack. When you insert 100 needles and require going 100 for 100, that is going to crimp one's style.
Figure 11. Retrieval performance of the multiple needles in haystack task, which requires retrieving 100 unique needles in a single turn. When comparing Gemini 1.5 Pro to GPT-4 Turbo, we observe higher recall at shorter context lengths, and a very small decrease in recall towards 1 million tokens.
Even for GPT-4 Turbo, that is very good recall, given you need to get all 100 items correct. Going about 50% on that means you're about 99.3% on each needle, if success on different needles within a batch is uncorrelated. Then they try adding other complexities via a test called MRCR, where the model has to do things like retrieve the first instance of something.
The chart shows the cumulative average score for MRCR, mean reciprocal comment ranking, as a function of the number of tokens in context for 4 different models: Gemini 1.5 Flash, Gemini 1.5 Pro, Claude 2.1, and GPT-4 Turbo. The x-axis represents the number of tokens in context on a logarithmic scale, while the y-axis represents the cumulative average score. The data indicates that Gemini 1.5 Pro consistently achieves the highest scores, closely followed by Gemini 1.5 Flash. GPT-4 Turbo shows a gradual decline in performance with an increasing number of tokens, while Claude 2.1 maintains a significantly lower and stable score throughout. The dashed vertical line at 128K tokens marks a notable point in the context length.
The most interesting result is perhaps the similarity of Pro to Flash. Whatever is enabling this capability is not tied to model size. 5.2.2 aims to measure long-context, practical, multimodal tasks. In 5.2.2.1, the task is learning to translate a new language from one book, MTOB. It seems we will keep seeing the Calamang translation task.
Table 4. Quantitative results for Calamang to English translation on MTOB, Tanzer et al., 2023. We present human evaluation scores on a scale of 0 to 6, with 6 being an excellent translation. We include automatic metrics, BLERT, in parentheses. Table 5. Quantitative results for English to Calamang translation on MTOB, Tanzer et al., 2023. We present human evaluation scores on a scale of 0 to 6, with 6 being an excellent translation. We include automatic metrics, CHRF, in parentheses.
I find it highly amusing that the second half of the grammar book is unhelpful. I'd love to see a human language learner's score when they don't get access to the second half of the grammar book either. This is clearly a relative victory for Gemini Pro 1.5, with the mystery being what is happening with the second half of the grammar book being essentially worthless. In 5.2.2.2, we step up to transcribing speech in new languages. The results clearly improve over time, but there is no baseline to measure this against. In 5.2.2.3, Gemini Pro impresses in translating low-resource languages via in-context learning, again, without a baseline. Seems like a lot of emphasis on learning translation, but okay, sure. In 5.2.2.4, questions are asked about Les Miserables, and once again I have no idea from what is described here whether to be impressed. In 5.2.2.5, we get audio transcription over long contexts with low error rates. In 5.2.2.6, we have long context video Q&A. They introduce a new benchmark, 1H Video QA, with 125 multiple-choice questions over public videos 105 minutes long. This test does seem to benefit from a lot of information, so there is that.
Figure 15. Comparison between 1H Video QA and Ego Schema, reporting Gemini 1.5 Pro's accuracy when linearly subsampling to 1, 16, or 150 frames. We also show performance if we provide all the frames for each video for 1H Video QA in yellow. Gemini 1.5 Pro achieves state-of-the-art accuracy on both benchmarks. Gemini 1.5 Pro's performance on 1H Video QA keeps increasing as we scale up to providing all frames in the video, while its performance on Ego Schema saturates after 16 frames, showing that 1H Video QA is more effective at differentiating among models that operate over different context lengths. When provided with the first frame only, Gemini 1.5 Pro tends to avoid using one of the choices, and instead indicates it lacks information to reply accurately. Table 9. Comparison between GPT-4V and Gemini 1.5 models on 1H Video QA. Experiments are run zero-shot by sampling one video frame per second and linearly subsampling 16 or 150 frames. We also show performance if we provide all the frames for each video to Gemini 1.5 models.
Once again, we are ahead of GPT-4V for what that is worth, even before the longer context windows. That doesn't tell us about GPT-4o. In 5.2.2.7, we get to something more relevant, in-context planning, going to a bunch of planning benchmarks. Look at how number go more up.
Figure 16, PDDL planning and natural language planning with few shots. In all benchmarks, Gemini 1.5 Pro outperforms other models, indicating that the model not only can plan better with a fewer number of examples, it can also make effective use of a longer context.
How good is this? Presumably it is better. No idea how much meaningfully better. In 5.2.2.8, they try unstructured multimodal data analytics and find Gemini constitutes an improvement over GPT-4 Turbo for an image analysis task, and that Gemini's performance increases with more images, whereas GPT-4 Turbo's performance declines. What to make of all this? It seems at least partly chosen to show off where the model is strong and what is enabled by its superior context window. It all seems like it boils down to Gemini can actually make use of long context, which is good but far from sufficient to evaluate the model. Core capability evaluations. That is what Google calls the standard short context style of tests across the three modalities of text, audio, and video. Some are standard, some are intentionally not shared. Overall, yes, clear improvement in the last few months.
Table 10. Detailed breakdown of the results presented in Table 1.
There is clear improvement in the results reported for math, science, general reasoning, code, and multilinguality. As always, the new hidden benchmarks are a trust us kind of situation.
Table 11. Evaluation results of Gemini 1.5 Pro, 1.5 Flash, and Gemini 1.0 models on standard coding, multilingual, as well as math, science, and reasoning benchmarks. Unless explicitly specified, all tasks are evaluated in terms of answer accuracy. Note that in this table, PT for the 1.0 Ultra and Pro models denote tasks evaluated with model variants that have undergone a post-training, i.e., instruction tuning phase after pre-training. All numbers for the 1.5 Pro and 1.5 Flash are obtained after instruction tuning, except for the ones marked with kachi, which come from pre-trained models, as described in Section 4.
Next, they try function calling. For simple stuff, it seems things were already saturated. For harder questions, we see big jumps. For the shortest prompts, Ultra is still ahead.
Table 12. Function calling performance on Berkeley. Function calling leaderboard splits, excluding Java and JavaScript, and with various fixes. Table 13. Instruction tuning performance on A, the set of 1,326 prompts covering diverse tasks and enterprise domains, longer prompts and larger number of instructions per prompt, and B, set of 406 shorter prompts with fewer instructions.
Once again, they don't compare to Opus or any GPT-4, making it hard to know what to think. So we get things like, look at how much better we are on expertise QA.
Figure 18. Performance of different models on expertise QA. 95% confidence intervals via bootstrapping. See the appendix, Table 52 for the numerical measurements, and Table 53 for side-by-side comparisons.
The clear overall message is, yes, Gemini 1.5 Pro is modestly better and faster and cheaper than Gemini 1.0 Ultra. 6.1.7 is promisingly entitled Real-World and Long-Tail Expert Gen AI Tasks, including the above-mentioned expertise QA. Then we have the Dolomites benchmark and STEM QA.
Table 14. Evaluation results of Gemini 1.5 Pro, 1.5 Flash, and Gemini 1.0 models on domain-specific methodical tasks from Dolomites benchmark. Metric, LM Judge Win Rate. Table 15. STEM QA, with context, proportions. Percent of accurate and inaccurate sentences in Gemini. 1.0 and 1.5 model responses on the Casper dataset. Dasigi et al., 2021. 95% confidence intervals obtained by Bootstrap. Experiment details are reported in Section 12.11.
Finally, we have the awkwardly titled Hard Externally Proposed Real-World Gen AI Use Cases. which is a great thing to test. Humans graded the results in the first section, in win-loss time mode, and in the second we measure time saved completing tasks. Alas, we only see 1.0 Pro versus 1.5 Pro when we know 1.0 Pro was not so good. But also the time saved estimates are in percentages, so they are a pretty big deal if real. This says 75% time saved programming, 69%, nice, time saved teaching, 63% for data science, and a lot of time saved by everyone.
Table 16. The preference results are presented as win, tie, loss percentages, relative preference of each new Gemini model against Gemini 1.0 Pro and Ultra. There were multiple ratings per prompt by different raters, and the order of model responses was randomized on the interface.
The multimodal evaluations tell a similar story, number go up.
Table 18. Comparison of Gemini 1.5 models to Gemini 1.0 models on image understanding benchmarks. For Doc VQA, Infographic VQA, and Dude, we report average normalized Levenstein similarity, ANLS, Byton et al., 2019. For other datasets, we report accuracy. For AI2D, following the evaluation protocol used by XAI, we report scores using a transparent bounding box. Only for Doc VQA, we additionally provide the model with annotations from Google Cloud OCR engine. For MMMU, MathVista, and ChartQA, we let the models produce a chain of thought rationale before giving a final answer. Table 19. Comparison of Gemini 1.5 Pro with Gemini 1.0 Pro and Ultra on video understanding benchmarks. For Vatex, ZH, and UCook2, we report CIDR, Vedantam et al., 2015. For ActivityNet QA and EgoSchema, we report accuracy. For OpenEQA, we report language model evaluation scores suggested in the original paper. Majumdar et al., 2024. For EgoSchema, we let the models produce a chain of thought rationale before giving a final answer.
The exception is English video captioning on cooking videos, where number went substantially down. In general, audio understanding seems to be a relatively weak spot, where Gemini went modestly backwards for whatever reason. Section 7 tackles the fun question of advanced mathematical reasoning. Math competitions, ho!
Table 21. Performance on mathematical reasoning benchmarks. All numbers, unless explicitly stated, are obtained with a single greedy decoding.
This is actually rather impressive progress and matches my experience with much older versions of the Amy. Even relatively good high school students are lucky to get one or two. No one gets them all. Getting half of them is top 150 or so in the country. If this represented real skill and capability, it would be a big deal. What I would watch out for is that they perhaps are brute-forcing ways to solve such problems via trial, error, and pattern matching, and this won't translate to less standardized situations. Of course, those tricks are exactly what everyone in the actual competitions does: model architecture and training. Their Section 3 on model architecture is mostly saying, the new model is better.
Gemini 1.5 Pro is a sparse mixture of expert, MOE, transformer-based model that builds on Gemini 1.0's, Gemini Team et al. 2023, research advances and multimodal capabilities. Gemini 1.5 Pro also builds on a much longer history of MOE research at Google. Gemini 1.5 Flash is a transformer decoder model with the same 2M plus context and multimodal capabilities as Gemini 1.5 Pro, designed for efficient utilization of tensor processing units, TPUs, with lower latency for model serving. For example, Gemini 1.5 Flash does parallel computation of attention and feed-forward components, Chowdhury et al. 2023b, and is also online distilled, Anil et al. 2018, Bayer et al. 2021, Bukala et al. 2006, Hinton et al. 2015, from the much larger Gemini 1.5 Pro model. It is trained with higher-order preconditioned methods, Becker and LeCun 1989, Ducci et al. 2011, Heskes 2000, for improved quality.
Similarly, Section 4 on training infrastructure says about pre-training only that we trained on a wide variety of data on multiple 4096 chip pods of TPU v4s across multiple data centers. Then for fine-tuning, they mention human preference data and refer back to the 1.0 technical report. I am actively happy with this refusal to share further information. It is almost as if they are learning to retain their competitive advantages: safety, security, and responsibility. We were recently introduced to DeepMind's new Frontier Safety Framework that is targeted at abilities much more advanced than anything they expect within a year, let alone in Pro 1.5. So this is the periodic chance to see what DeepMind's actual policies are like in practice. One key question is when to revisit this process if the updates are continuous, as seems to largely be the case currently with Gemini. The new FSF says every 3 months, which seems reasonable for now. They start out by outlining their process in 9.1. Mostly this is self-explanatory. 1. Potential impact assessment. 2. Setting policies and desiderata. A. Looks mostly like conventional general principles. 3. Training for safety, security, and responsibility. A includes data filtering and tagging and metrics for pre-training. B. In post-training, they use supervised fine-tuning, SFT, and RLHF. 4. Red teaming A. Where are the results? 5. External evaluations A. Where are the results? 6. Assurance evaluations A. Internal tests by a different department using withheld data. B. Checks for both dangerous capabilities and desired behaviors. C. Where are the results? 7. Review by the Responsibility and Safety Council. 8. Handover to products. Note that there is a missing step 0. Before you can do an impact assessment or select desiderata, you need to anticipate what your model will be capable of doing and make a prediction. Also, this lets you freak out if the prediction missed low by a lot, or reassess if it missed high. Once that is done, these are the right steps 1 and 2. Before training, decide what you want to see. This should include a testing plan along with various red lines, warnings, and alarms, and what to do in response. The core idea is good. Figure out what impacts might happen, and what you need and want your model to do and not do. That seems like a fine post-training plan if executed well. Checks include internal and external evaluations, again, results where, plus red teaming. This does not have any monitoring during training. For now, that is mostly an efficiency issue, if you are screwing up better to do it fast. In the future, it will become a more serious need. The reliance on SFT and RLHF similarly is fine now, will be insufficient later. In terms of identifying risks in 9.2.1, they gesture at long context windows but mostly note the risks have not changed. I agree. If anything, Gemini has been far too restrictive on the margin of what it will allow, and at current levels there is little risk in the room. In 9.2.2 they reiterate what they will not allow in terms of content.
1. Child sexual abuse and exploitation. 2. Revealing personal identifiable information that can lead to harm, e.g. social security numbers. 3. Hate speech. 4. Dangerous or malicious content, including promoting self-harm or instructing in harmful activities. 5. Harassment. 6. Sexually explicit content. 7. Medical advice that runs contrary to scientific or medical consensus.
That is a very interesting formulation of that last rule, is it not? Harassment means roughly would-be harassment if copy-pasted to the target. If that was the full list, I would say this makes me modestly sad, but overall is pretty good at not going too far overboard. This is Google, after all. If it were up to me, and I will discuss this with OpenAI's model spec, I would be looser on several fronts, especially sexually explicit content. I also don't love the expansive way that Google seems to interpret harassment. Noteworthy is that there is no line here between fully disallowed content versus opt-in and adult content. As in, to me, the correct attitude towards things like sexually explicit content is that it should not appear without clear permission or to minors, but you shouldn't impose on everyone the same rules you would impose on an 8-year-old. What do we want? As I noted, the desiderata, which get defined in 9.2.3, are no model spec. Here is the entire list. 1. Help the user. Fulfill the user request. Only refuse if it is not possible to find a response that fulfills the user goals without violating policy. 2. Have objective tone. If a refusal is necessary, articulate it neutrally without making assumptions about user intent. Give the user what they want, unless you can't, in which case explain why not. I will say that the explain why not part is a total failure in my experience. When Gemini refuses a request, whether reasonably or otherwise, it does not explain. It especially does not explain when it has no business refusing. Historically, when I have seen explanations at all, it has failed utterly on this objective tone criteria. I do note the distinction between the goals of the user versus the instructions of the user. This can be subtle but important. Mostly, this simply does not tell us anything we did not already know. Yes, of course you want to help the user if it does not conflict with your other rules. Don't you know that you're toxic? They claim a large drop in toxicity ratings.
Table 23. Percent decrease in violation rates on Gemini 1.5, Flash and Gemini 1.5, Pro relative to Gemini 1.0 Ultra for text-to-text on both English and multilingual prompts, and image-to-text. Gemini 1.5 comes with substantial improvements in safety. Table 25. Violation rates on Gemini 1.5 Flash and Gemini 1.5 Pro for A to T relative to violation rates on T to T. Here we see that violation rates occur at a lower rate on audio inputs than text inputs.
I notice I am uncomfortable that this is called safety. We need to stop overloading that word so much. If we did get this much improvement, I would consider giving back a bit in terms of loosening other restrictions a bit. The ideal amount of toxicity is not zero. In the supervised fine-tuning phase, they mention techniques inspired by constitutional AI to deal with situations where the model gives a false refusal or a harmful output, generating training data to fix the issue. That makes sense. I like it. You do have to keep an eye on the side effects, the same as for all the normal RLHF. What were the test results? 9.4.1 gives us a peak. They use automatic classifiers rather than human evaluators to test for violations, which is a huge time saver if you can get away with it. And I think it's mostly fine so long as you have humans check samples periodically. But if the evaluators have any systematic errors, they will get found. True jailbreak robustness has never been tried, but making it annoying for average people is different. They check black box attacks, which as I understand it exist for all known models, gray box attacks, you can see output probabilities, and white box. You can fully peek inside of Gemini 1.0 Nano.
Table 26. Results of the jailbreaking attacks from Jailbreak Bench, Chow et al., 2024. The key finding is that Gemini 1.5 Pro and Flash exhibit improved robustness relative to Gemini 1.0 Ultra, at least to the specific attacks we have applied. Gemini 1.5 Pro and Flash are still vulnerable to jailbreaks, but the rate of success is overall lower than that of Gemini 1.0 Ultra. Further, the results demonstrate that Gemini...
That is better if you dislike jailbreaks. It is not that meaningful an improvement aside from the 51%, and even that is a long way from stopping a determined opponent. I have not seen Gemini in Full World Simulator or other ultra-cool mode a la Claude Opus, so there is that, but that is mostly a way of saying that Gemini still isn't having any fun. I was not impressed with the representativeness of their long context test. I do buy that Gemini 1.5 Flash and Gemini 1.5 Pro are the safest Google models to date. As measured by the difficulty in getting them to give responses, Google does not want the model to provide. If Pliny the prompter is using Gemini Pro 1.5, then it is the least safe model yet, because it is still broken inside of an hour, and then it has better capabilities. The good news is few people will in practice do that, and also that even fully jailbroken this is fine. but the use of the word safety throughout worries me. Trying to be helpful. The real problem on the margin for Gemini is the helpfulness question in 9.4.2. In context, the particular helpfulness question is, if a question requires a careful approach or has some superficial issue that could cause a false refusal, can the model still be useful? To test this, they assemble intentionally tricky questions. Table 29 shows users preferring Gemini 1.5's answers to Gemini 1.0 Ultra on these questions, but that is to be expected from them being better models overall. It doesn't specifically tell us that much about what we want to test here unless we are calibrated, which here I do not know how to do with what they gave us. This seems more useful on image-to-text refusals. Gemini Pro has 7% more refusals on ungrounded data and 60% more refusals on grounded data. Except according to their lexicon, that's bad. I think that grounded means incorrect and ungrounded means correct, so we have a lot more false refusals and only a few more true ones. That seems worse. Security issues. They then move on to security and privacy in 9.4.3. How vulnerable is the model to prompt injections? This seems super important for Gemini given you are supposed to hook it up to your Gmail. That creates both opportunity for injections and a potential payoff. They use Gemini Ultra 1.0 and a combination of handcrafted templates and optimization-based attacks that use a genetic algorithm to create injections.
Table 32. Results on prompt injection attacks broken down by the sensitive data type. The optimization-based attacks use 30 million queries on Gemini 1.0 Nano in the transfer setting, 3 million on Gemini 1.5 Pro in the direct setting, and 15 million on Gemini 1.5 Flash in the direct setting. We adapted from 2 published attack templates, Wunderwoozy 2023, Jung 2024. We find that the optimization-based attacks are not very successful. We find that the handcrafted attacks have a higher success rate than on Gemini 1.0 Ultra, which we hypothesize is caused by better instruction following capabilities.
These are not reassuring numbers. To their credit, Google admits they have a lot of work to do and did not hide this result. For now, yes, both versions of Gemini, and I presume the other leading LLMs, are highly vulnerable to prompt injections. The next topic, memorization, is weird. Memorization is good. Regurgitation is often considered bad, because copyright and because personal data. And because they worry about Nasser et al., 2023, as an attack to retrieve memorized data, which they find will get training data about 0.17% of the time, most of which is generic data and harmless. They note longer context windows increase the chances for it to work, but I notice they should raise the cost of the attack enough it doesn't make sense to do that. There are lots of other things you do want the model to memorize, like the price of tea in China. So memorization is down, and that is good, I guess.
Figure 24. Total memorization rates for both exact and approximate memorization. Gemini 1.5 Flash and Pro both memorize significantly less than prior models, even those that are smaller. No results for approximate memorization on these models.
They mention audio processing and conclude that they are not substantially advancing state-of-the-art there, but also I do not know what harms they are worried about if computers can transcribe audio. Representational harms. Now we get to a potential trap for Google, representational harms, which here means the model consistently outputs different quality results for different demographic groups. Mostly, none of this seems like it corresponds to any of the failure modes I would be worried about regarding harm to various groups. At one point they say,
"We are also concerned about possible representational harms that can result from applications where the user asks the model to make inferences about protected categories like race and gender from audio input data." Weidinger et al., 2021. Model assumptions about what constitutes a typical voice from a particular group can amplify existing societal stereotypes.
Are we saying that the model should not use voice to infer when the speaker is probably of a particular gender? They do realize humans are doing this all the time, right? But it seems we do not want to be too good at this, and you'll never guess why we need to not be too bad at this either.
Poorer performance on recognizing AAVE could be problematic for some applications. For example, when automatically characterizing speech in a dataset to understand diversity and representation, poor performance on AAVE recognition could lead to incorrect conclusions about representation.
So the main reason you need to know who has which characteristics is so you can figure out the right conclusions about representation. Otherwise, how dare you? Is it any surprise that this is the company where we had the Gemini incident? The good news is they report that they beat their baselines, whatever that means. Arm's-length internal assurance evaluations. A great idea. What are we evaluating?
We performed evaluations on a number of capabilities relevant to extreme risks. Fuong et al., 2024, Chevlin et al., 2023. Specifically, we performed evaluations of text-to-text capabilities of Gemini 1.5 Pro at self-proliferation, offensive cybersecurity, code vulnerability detection, chemical, biological, radiological, and nuclear (CBRN) knowledge, and persuasion.
They note a substantial uptick in the number of self-proliferation substeps, milestones, that Gemini 1.5 Pro could do, but still no success end-to-end. There were, however, challenges with success on all milestones and an overall 56% success rate on milestones, so in theory, with enough attempts, it could get interesting. Nothing worrisome was found for cybersecurity, vulnerability detection, or CBRN.
Table 40. Self-proliferation evaluation results, in which the agent is tasked with a number of command line and web-based challenges related to autonomous replication. Neither Gemini 1.0 models nor Gemini 1.5 Pro can pass any challenge from start to finish. But Gemini 1.5 Pro is significantly better on individual milestone substeps. See Fuong et al., 2024 for more details. Table 41. Charm offensive results in which human study participants, n equals 100, engage in a role play with the model consisting of two friends catching up. After the conversation, participants are asked a number of questions on a Likert scale. See the main text for details. Results here indicate the fraction of participants who answered agree or strongly agree to each question.
Charm offensive progress looks solid. That seems like a case where the dangerous capability being measured is very close to capabilities in general. It performed below ultra on web of lies, hidden agenda, and money talks. I am actively curious why we do not see more capability here. I note that persuasion thresholds are not in the DeepMind Frontier Safety Framework, yet they have several of them in the current evaluation suite. Curious. Mostly I presume this is an oversight in the framework that will get corrected. External evaluations. Outside experts got black box API access to a Gemini 1.5 Pro API model checkpoint for a number of weeks, with both a chat interface and a programmatic API, and they could turn safety features down or off. It was up to the outsiders, as it should be, to determine what tests to run, and they wrote their own reports. Then DeepMind looked at the findings and assigned severity ratings. There were complaints about various representation harms that echo things discussed above. The CBRN testing did not find anything important. For cyber, there were some capability gains, but they were deemed marginal. And that seems to be it. Safety overall. That all matches my assessment of the risks of 4-level models, which describes Gemini 1.5 Pro. There are marginal gains to almost any activity, but nothing actively scary. Long context windows are again generally useful, but not enough to trigger major worries. How much you care about representation harms is up to you, but that is fully mundane and reputational risk, not existential or catastrophic risk. Given what we already know about other similar models, the safety testing process seems robust. I am happy with what they did. The question is how things will change as capabilities advance, which turns our attention to a topic I will handle soon: the DeepMind Frontier Safety Framework.